Good evening to all students. We'll continue with our classes. Today is the last lecture class, and we'll be discussing about range data images in this class. We'll first begin with what are range sensors or what is range data, and then we'll move on to see some of the image processing techniques or computer vision techniques with regard to the range data, like for example, segmentation or edge detection, and then we'll move on to how registration is done on range data. So what is range data, or what do you mean by range images? So basically these are depth images. That means images in which there is depth information regarding a particular object or a certain set of objects in a particular scene. Okay, so usually when you go with normal images, normal RGB images, which are color images or grayscale images, what we try to capture is what is the different color intensity which is present in those images, right? In the case of depth images, it is not these intensity values or the brightness levels which are being captured. Rather than that, in the depth images, it means that you're trying to find out what is the relative depth between different objects which are present in the image. Okay, and depending upon the depth, you'll have different values which are assigned to different pixels in the images, right? So this such an information becomes useful when let's say when you're working with video sequences where you need some motion information, or with regard to tracking applications, or with regard to any applications which requires 3D reconstruction. We require this depth information. Okay, and in such applications range images would help. Okay, and the depth images, it is exactly the desired output of the stereo reconstruction, or the SFM, or all 3D reconstructions. Because in 3D reconstruction also, what you're trying to do is you're trying to reconstruct the 3D point of the scene, right? So similarly in depth images also, what it is trying to see is how much is the depth information, or there also it is trying to find out the relative positions of the 3D points in the image. Now, how do you achieve this? So for this, you have specialized sensors, which you can call as the active range sensors, and there are different types of range sensors, which are specifically designed in such a way that it can capture these kind of depth information of different objects. Okay, and one such sensor, range sensor, is the triangulation-based range finders or range sensors. So how that works is very similar to the epipolar geometry that we were discussing about, or the pinhole camera concept. Okay, so in that case, when we were discussing about binocular fusion, okay, or binocular reconstruction, we saw that what we used where there were two cameras. So you used to have one camera here and another camera here, and from these two cameras, okay, you were trying to image the particular 3D point which is present in the scene, right? So instead of one of the cameras, what you're using is a laser over here. So it's like you're using a laser, okay, or a light source, okay, and this light source would provide the light, or it will reflect the light onto the 3D object, and from which you try to get the image of that particular point. Okay, so the concept is similar here, where you have you're trying to project or trying to project this light onto the 3D point over here, and you're able to you're trying to find out what is this relative position of this 3D point here. Okay, and we prefer lasers here because it gives a more focused light source, and it will if you're using any other light source, what happens is there would be there would be some kind of a blurring because it would be spread apart. The light would be spread apart, whereas if it's a laser, it would be concentrated towards that particular object or point that we are trying to focus on, or we are trying to image. So here, as I said, you have the camera, you have the illuminant, and these are the the points which are corresponding to the 3D points, okay, on these planes over here. And let's say you're considering a point over here, right? And you're considering another point over here. Now, what you're trying to do is we are trying to find the location of these two, or the set of points on the surface, right? So if you look at an example, you can think of it this way. Let's say you're projecting a particular light pattern. Okay, so when you're projecting this light pattern, what happens is, depending upon how much or how much of it is reflected back and reaches the camera, you get an information on how much is the depth of each of those points. Okay, and this is an illustration showing how the camera image would look like. So in active range sensors, okay, as I said here, what we're using is another light source or an illumination source over there, and you're using a laser pointer, right? But there are some disadvantages of using these active range sensors using triangulation. So some of the disadvantages is that you might need to use multiple cameras in order to improve the accuracy of the particular method that we are of this particular method. Okay, and the acquisition speed is kind of less. Okay, and when you're using a laser spot or a laser light source, what happens is sometimes you may miss upon some data points. Okay, there might be some occlusions which happen because of the object itself. Okay, and there are chances of erroneous data also which is occurring. Okay, and there are some other difficulties with respect to the using the laser itself during the scanning process. Okay, and so instead of using triangulation based scanners, okay, you can go with other more advanced techniques or much better techniques with better accuracy, and we'll be discussing about some of those techniques later. So this is an example of a range data which has been captured by the Minolta Vivid scanner. So this is basically a triangulation based sensor, range sensor. Okay, and these are just two different views that we see. So we can clearly make out that the shape of the rabbit has been very faithfully reconstructed, right? Okay, so there are other types of range sensors also, which helps to overcome the limitations of the triangulation based sensors. And the second approach that we're going to see involves the use of a transmitter, a receiver, and some kind, some hardware. Okay, so basically what you're using is you have a transmitter at one point and a receiver at the other point, right? So you're trying to measure how much is the time of flight, and by measuring how much time it takes to reach, or the time of flight of the particular signal that has been transmitted, by measuring the time of flight that it receives after reaching the receiver, you get an information of how much of depth is present, right? And based on that you can reconstruct a particular the shape of the particular object. And when we are talking about time of flight laser range sensors, okay, as I said, this is different from triangular based sensors. When you're going ahead with a time of flight range sensors, there are again different types depending upon what is it that you are transmitting. Okay, so you may be transmitting some pulse time, maybe a signal of or a train of pulses. Okay, so if it is measuring the time with the help of laser pulse, then that type of time of flight, a laser range sensor, can be called as the pulse time delay. So similarly, you also have the AM phase shift, where if you are making use of the amplitude modulation. If you're making use of the frequency modulation for this, then you have the FMB. So these are the different quantities or measures that we try to determine, or that we are measuring at the receiver's end, in order to determine how much is the depth of that particular object. Okay, and compared to triangulation based systems, the advantage of the time of flight sensors is that it will have a more operating range. Okay, so usually triangulation based systems shows good results only if the objects are kind of nearer to the cameras. Okay, otherwise if it's a laser point, what happens is if the distance increases, that the light kind of disperses, right? So when you're using time of flight sensors, it has the advantage that even if the objects are further away from the camera, it still gives better results as compared to triangulation based sensors. Okay, so here you can again see some examples of the images which has been reconstructed using the time of flight sensors. Now, if you look at this image, we see that okay, this is the colored image, or let's say this is the actual object that we are trying to find the range data of. Okay, and here towards the left, what you see is a depth image, right? So in this depth image or the range image, what you have to note is that here those gray level values, it is not corresponding to the exact intensity values with respect to the particular object. Okay, it is the intensity values that you see over here, or basically the values that you see over here is the depth information. Okay, so higher pixel intensities or higher values shows that that particular object is present much closer to the camera as compared to the objects which have got darker values. Okay, like for example, if you look at this image, you know that the object which is closest to the camera is basically the hands, right? These joint hands. And similarly, you see in the range data also that this joint hands shows the highest intensities. Okay, and that is because it is present as close to the camera as possible. Okay, so this is one. One thing you have to remember in the case of range data. Okay, where the information regarding the depth can be easily identified, okay, by with the help of different sensors, range sensors. And what the range sensors does is it will try to identify what is the depth information, and the closer the object is to the camera, you have higher or brighter intensity values, or values which are being assigned. Okay, now let's see. So having captured a range data or a range image, how do we do a segmentation? So what will be by segmentation? What we'll be saying here is basically edge detection. That is, how will you be able to identify the edges of the objects in the range image? Okay, so we'll look at some examples over here. So before that, we need to find out, or we need to learn about certain properties of curves and surfaces, and after that we'll be going to a method by which you can do edge segmentation or edge detection in range data images. So let us first see about differential geometry. So basically differential geometry means it is to model the shape of objects. Okay, so it can be curves or surfaces or so on, right? So the study of which we try to learn how to model different shapes of objects is what we call as differential geometry. And we'll just look at quickly go through some basics, right? So when it comes to curves, you can represent curves in different forms or in different ways. So first is the parametric form. In the parametric form, you can see that this is how you express it. You can write P is equal to XYZ is equal to X of t, Y of t, Z of t. Okay. So that means now here you can represent, there is only a single parameter t present for a curve by which you can you can represent the shape of the curve. Okay, that is by varying this value of t within, let's say, t naught to t1. By varying the value of t, you will be able to obtain the shape of the curve. That means if you just imagine there is a curve over here, you can imagine that basically you're trying to find out the different points along the curve. Okay, so the points on the curve can be determined by varying this parameter t in the case of curves, right? Now there is also another representation for the curves, okay, and it's called as the implicit representation. So by implicit representation, you can represent it as f of x, y, z is equal to 0. Now, when it comes to surfaces, okay, just like curves, you can also represent surfaces in different forms, the parametric form, the implicit form, the explicit form, and so on. So, in the parametric form of a surface, you can represent it by xuv, yuv, and zuv. So, what you notice is that for the curves, you have only one parameter. In the case of, a surface, you have two parameters which are used to describe the surface, and those parameters are u and v, right? So like if I just let's say if I'm varying u from u0 to u1 and v from v0 to v1, the point on the surface keeps changing, or the shape of the surface keeps changing, right? And depending on that, we are actually trying to model the shape of the surface by varying the parameters u and v. And other representations of the surface is the implicit representation, where you can write f of x, y, z is equal to 0. And another representation is the explicit representation, where I can write z is equal to fxy. Okay, so these are all different ways by which you can represent the surface. Okay, so let's say for range images, we usually go for the explicit, form of writing or describing the surfaces. Okay, so range image is a rectangular grid of samples of a surface, which is given by z is equal to fxy. So this xy can be thought of the image plane coordinates. Okay, and z is basically the distance which is parallel to the z axis in the camera coordinates. So let's just take an example over here. Okay, so here we can see this is a UV parameter plane. Okay, and in this parameter plane, you above, with respect to this parameter plane, you have a surface, right? And let's say we are considering some particular point on the surface. Okay, so here what we see is the normal to the surface, which is given by this expression n is equal to xu into xv by your modulus of xu into xv, right? And you let's say I have another point over here, right? So I can represent it by xuv plus the x, right? So here what I do is, as I'm changing the point, as I'm changing the location of the point, let's say if I'm moving to the left or if I'm moving the point to the right, what happens is you can see the shape of the surface keeps changing. So if you look at this bend, what happens is, now this is kind of the topmost part. So if I'm moving to the left, it's kind of drooping down, so you get a different location over here, right? And the shape of the surface is changing, right? So in differential geometry, what we do is we try to vary the values of u and v, by which what happens is the position of the point on the surface keeps changing, right? And not just the position, but also the first derivatives, which is given by pu and pv, and also the surface normal, everything changes. So by measuring all this, we'll be able to describe what is the shape of a particular surface. Okay, so here for the parameterization of a surface map, okay, you can represent this way. You can write it as PUV is equal to XUV, YUV, and ZUV, right? And as I said, the first derivatives can be written as PU, okay, P suffix U, UV, because they are functions of UV, and P suffix V, UV, right? Now this PU and PV, they are basically called as the tangent vectors. Okay, and this is also an important, tangent vectors are important in order to determine the or describe the shape of the surface. Okay, so again, in order to find the surface normal, okay, it is defined as the unit vector which is normal to the tangent plane at the point. So let's say I have a point over here, right? So along this point I have tangent vectors, okay, which are given by pu and pv. So this surface normal is basically normal to the tangent plane, okay, the plane which is tangent to with respect to that particular point, that is the surface normal, okay. And you can compute the surface normal this way. I can compute it as pu cross pv divided by pu cross pv, taking the double modulus of that, or taking the norm of that, right? So here what you're doing is we're trying to express the surface normal in terms of the first derivatives of, or the tangent vectors, or the first derivatives pu and pv. Okay, so these tangent vectors pu, pv and the surface normal which is given by n, uv, they both together describe the shape of the surface, right? And while describing the shape of the surface, what we are trying to find out is how much is the curvature of the surface, right? So in order to know the curvature of the surface, we need to measure certain points. We need to measure where is the position of the point, or the tangent vectors and the normal, etc., right? And we also need to find out this particular plane over here, okay. So this plane that you see, okay, it contains the normal, okay. At the same time, it is intersecting through the point which we are considering on the surface, right? So such a plane is what you call as the normal curvature. So normal curvature at the point P is defined as a curvature of the planar curve of intersection. And here you can see that this particular plane, it intersects the point P over here, right? Now it's not just a normal curvature. So here, as you change the position of the point P, as you're moving P to the left or right, what happens is this plane, the normal plane, the normal curvature, because basically the normal as well as the tangents also changes, right? So as the tangent vectors in the normal changes, with moving the points accordingly, the normal curvature and the plane, normal plane curvature keeps changing, right? So what we are actually doing is we try to find out what is the minimum and the maximum curvatures, right? After varying the position of the points, we try to find out the minimum and maximum curvatures, and these are called as the principal curvatures, okay. And once you know the principal curvatures, by finding the product of the principal curvatures, I can find out what is the Gaussian curvature, okay. And the Gaussian curvature is given by k is equal to k1, k2, where k1 and k2 are the principal curvatures, okay. And I can also find out another parameter which is known as the mean curvature. Mean curvature is basically the average of the principal curvatures. Now this Gaussian curvature, mean curvature, etc. are the quantities that can be used to measure the overall shape of the object. Now let us go to range data segmentation. So segmentation means it is basically what we are discussing is the edge detection. That is, how do you detect the edges present in the range data? Okay. So in the previously what we have seen is, if you wanted to find the edges, okay, all that you do is you try to subtract between different intensity values, okay, which are present within the neighborhood, and then if there is an abrupt change in the intensity values, you say that there is an edge. But that particular technique cannot be applied in the case of range data images, mainly because in the range data, what you have is not exactly the intensity values, okay, of the objects which are present there, right? It is not the exact intensity values of the objects which are present there. Rather, it is the depth information which is present in the range data, okay. So therefore, the method by which you find the edge detection has to be varied a little bit, right? So here, let us see how we can, find or detect edges in the case of range data images. So this is a method of finding the the edges in the range images, right? So here what we see is an example of a range image of a bottle, okay, and this is like after pre-processing and thresholding the background, etc. This is how we have obtained the range image of a particular bottle, and you want to find out what is the edge of the particular bottle. So let us see how we can go about this. So before that, we need to define what is an edge in a range data. As I said, it is not the same as edges in a normal color image or a grayscale image, right? So there are three types of edge models or edges. You can call that as steps, roofs, and shoulders. Okay, so steps means it is the actual depth. Okay, actual depth. When the actual depth is discontinuous, at that point we say there is a step. Roofs means the depth is continuous but the orientation changes, and shoulders is when it consists of two roofs and correspond to a step which is viewed obliquely. So this is an illustration of a step model and a roof model. Okay, so in the step edge, you can say that, let's say you have the values which are increasing, and at one particular point, so at this particular point you have a value, and suddenly it abruptly increases to another value here, and then it then starts decreasing from this value. So that means at this particular point of value of x, there is a sudden increase in the depth, right? So at this point the depth was c, okay, and at the very next point onwards it is coming to c plus h. So when there is an abrupt change in the depth information, you can call it as a step edge. Okay, now another type of edge you can define is the roof model. So roof model is when, let's say, the depth keeps increasing, okay, and then at some point it starts decreasing here. So that means basically the direction is changing. That is, it is still continuous. There is no abrupt change in the edge in the depth, okay, but you see that the direction changes. It was increasing and now it starts decreasing. Okay, so this kind of an edge discontinuity is what you call as the roof edge. Okay, so here this is an example of the range image on the left side, and the right side you can see the edges, that is the steps and roofs which have been identified in the same image. Okay, so here you can see this side there is a step because there is a sudden discontinuity in this case, but here this is a roof because you see that here it is moving from one direction, then the direction changes here, right? So therefore it's a roof. But here there is along the same path, you say that there is a sudden abrupt change in the depth information. Okay, so this is how you can identify steps and roofs, and basically steps and roofs are different types of edges in a range data image. Now, how do you find these steps and roofs? So we have defined what is step edge and what is roof edge, and how can you determine these presence of step and roof edges in range images. We'll just see that now. Okay, so what you can do is, the basic idea is, first you can try to smoothen the image using the Gaussian smoothing, okay, at different scales, and then you can go about by extracting significant features and then identify the edges. Okay, so we'll see how that is done. So here what we do is we are trying to identify the step edges by finding the zero crossings of the principal curvature. Okay, so as I said, this is the step model where it changes abruptly. Okay, and this is the roof model, right? So we can show the curvature, or we can express the curvature with the help of this particular equation. Okay, need not go in detail to this equation, but try to understand what this means or how this process is done, right? So what happens is, when this value, okay, it tends towards infinity, then as sigma tends to 0, indicating that the roofs can be found as local curvature extrema. So what we do is, for the step edges, we're trying to find out the zero crossings of the Gaussian curvature. Okay, so we know that Gaussian curvature is found from the principal curvatures, right? So if you know that it is a product of the principal curvatures. So then what you need to do is first find out this Gaussian curvature and then try to find out the zero crossings. So in order to find the zero crossings, then that means I have to take the first derivative of the Gaussian curvature and then equate it to zero. Okay, to find out the zero crossings, right? And for roof edges, what I need to do is for the dominant principal curvature which is present, okay, I need to find the extrema and that gives me the roof edge. Okay, so this is how you compute the step edge and roof edge from the range image, and for that you need to find out the curvatures, right? So once this is obtained, what you can do is you can also improve the method by using the Gaussian smoothing. Okay, so for Gaussian smoothing, what we do is, for example, if you look at this particular example, here this is a range data which is noisy. Okay, that means you can see that there is ideally it should have been flat here and flat in this way, but you see that there are some abrupt variations here as well as here, right? So this is the range data. Now if you're doing a Gaussian smoothing, we can see that it has kind of smoothened this way. Okay, but this is not the exact information that we need because it has smoothened the the step edges which are present here, but we do not need that. We needed to detect the edges but at the same time remove the noise which are present at the other places which are not the edges, right? So therefore a traditional Gaussian smoothing does not really work. Okay, so what we need to do is we need to identify these step edges, and we need to ensure that except at the discontinuities all the other places it should smoothen. Okay, but it should not affect the discontinuities. So if you have to follow that principle, or in order to achieve that particular concept, what you do is you can apply a method which is called as the computational molecules. Okay, so what we do is these are the computational molecules what is present here, right? So these are basically some kernels that is used. These are some linear kernels. What we do is these are combined together to form the convolution mask, right? And then that is used for convolving the different images. So when we are doing that, since each of these are in itself trying to identify the regions of high probability of having the edges, what happens is you are ensuring that such regions are not being smoothened up to a very high level. Okay, so we're trying to prevent the smoothing at the discontinuities which are present. Okay, so overall now how it will look like is when you use the computational molecules in order to filter the image. And prior to that you need to do the Gaussian smoothing also. So after Gaussian smoothing, use the molecules and try to convolve over the image. Then this is how the image or the resultant image would look like, and that is exactly that we want also, where all the other regions are kind of smoothened out, whereas the discontinuities are unaffected. Okay, so here what we are trying to do is we are trying to find out the step and roof edges in a range data, and the normal procedure of finding the edges doesn't work here because we are dealing with range data, right? So the edges are first defined using the step model and the roof model, and what we saw is if we use a Gaussian smoothing, it kind of blurs out the edges or discontinuities, and it will not help with the discontinuities, or the edges are not preserved, right? So what we do is we make use of a technique called as computational molecules, where you have already seen the structure of the computational kernels present in the computational molecules. Now you combining all those kernels together, you can form an averaging mask which will help to preserve the edges and at the same time smoothen out at other places. And this is how the result would look like. Now after that, what you do is once the surface has been smoothed, you can try to find out the step edges and the roof edges, right? By making use of gradients of or finding the gradients using finite differences, right? So we compute the derivative using finite differences, okay? And these are the different expressions for finding the finite differences, okay? And this is something that we've already seen in the previous classes. And once the derivatives are known, we can easily find out what are the principal directions and curvatures. So this is an example of finding the step and roof edges for different iterations. So what I say is that as the iterations keep increasing, you get better results, and finally this is for a higher iteration, you see that you are able to find out the edges in the form of steps as well as roofs properly. Okay. Now let's see how we can do a range image registration. So first what we saw is what is a range image. Second topic that we saw is how the range image segmentation is done, in the sense how do you detect edges in range images. The next topic we'll see is what is range image registration, or how is it done, right? So why do we need to register these range images? Now, as I said, it has got different applications in the manufacturing as well as entertainment industry. It can be used for tracking, it can be used for some kind of, let's say, animation movies or video games or so on. So for all of this, the range images play a very important role, and it is important to register the range images with other kinds of data, right? So what we will be seeing here is how image registration can be done. But before that, we have to, just get familiarized with a concept which is known as the quaternions, right? So in quaternions, what we see is it is a method by which you can represent a particular, vector, okay, vector in another form, like it would be used later on in one of the algorithms that we'll be using, okay. So here basically it provides a linear method for estimating the rigid transformation, okay. And how you represent this is the quaternion can be represented by the letter q here, right? And q is defined as there is a real part associated with it as well as a imaginary part associated with it, okay. So there is a real scalar part which is associated with q, and there is an imaginary vector quantity which is associated with q, right? And how you represent this is now some of the properties is, if I'm taking a plus alpha plus b plus beta, that means the I'm just trying to add up to q1 and q2, right? So what happens is it is equivalent to adding up the scalar quantities and the vector quantities separately, right? And if I'm, let's say, multiplying with lambda, which is the scalar quantity, then I can write it as lambda a plus lambda alpha. These are just some properties, and this is for multiplication. You can represent it this way. And if I'm trying to find the conjugate, I can write q is equal to a plus alpha. The conjugate becomes q bar is equal to a minus alpha, right? And other properties is that if I try to find the squared norm, okay, so q square here, I can write it as a square plus alpha square, okay. So what trying to do is I'm trying to take the square of the scalar quantity as well as the imaginary quantity separately. And this is one of the main important properties which will be useful to us later, right, when we are dealing with the range data. And that is this particular form. That is, let's say I have a vector quantity, okay, and let's say R is a rotation matrix. If I'm trying to multiply this vector quantity with a rotation matrix, I can also represent it as q alpha q bar, right? So here q and q bar, here q can be represented as q is equal to cos theta by 2 plus sine theta by 2 into u, right? And alpha is basically this vector quantity itself, right? So this particular property we'll have to we'll be using it later, where if you have a rotation matrix, okay, we rather instead of finding out r alpha, we just represent it as q alpha q bar. Okay, so here now let us look at how we can go about using using the range images for image registration. One of the very familiar techniques is by using the ICP method, that is the iterative closest point method. So ICP method is something which we have already seen earlier, right? So in the ICP method, what we do is we are basically doing a rigid registration between two images, right? So in the ICP method, first we try to find out, 2 points. We try to find out the closest among the 2 points. Then we calculate what is a rigid transformation, okay, which should be used for mapping the points onto their matches. And then finally, after calculating how much is the error, we again try to find out for the new image. We try to find out what is the closest point. Again, we calculate the transformation and then compute the displacement of the error, and so on, and we keep on iterating it, right, in until we obtain an error which is as low as possible, right? So this basic concept of ICP, the process of trying to find out which are the closest points, and then doing or finding the mapping of the rigid transformation and calculating the error and then repeating the whole process again, okay, this whole process of iterating all this, the process is the same as earlier, okay, but here it is not a grayscale image that you're dealing with. You're trying to work with a range data image. So since it is a range data image, what you need to remember is how we find out the closest points, or how exactly the rigid transformation is calculated, will be different from that of how we estimate for the grayscale images. Okay, so how do you find the closest point? What we do here is we can find out the closest point or the nearest neighbors using the KD trees. Okay, so you don't need to go through the details of this. So what we try to do is we are basically trying to find out what is the nearest neighbor. Okay. Now next is estimating the rigid transformation. So for a rigid transformation, you know that the rotation as well as a translation will be involved, okay? And our job is to find out this rotation as well as the translation that has occurred, right? So what we do is after estimating a rigid transformation and applying that, we get x dash, and we try to find out the error using the SSD approach. We try to find out the error using x dash minus rxi minus t, okay? That means what is the actual minus the warped, right? So we try to use the SSD error or the distance between the 2 points, okay, the matching point as well as the rotated and translated point, okay, and then we calculate how much is the distance of the error, and depending upon that we try to reduce that. So we again recalculate the closest points in the rigid transformation and recalculate the error here, okay. So here our aim is minimizing E, right? Now we know that we need to find out this rotated point, right? So in order to find that, we can make use of the quaternion approach here, right? So we can use that to minimize E. So what I can do is, instead of representing or instead of writing or determining ry here, I can just replace that by qy q bar, okay. And if q square is equal to 1, I can just take that norm here, right? And I can simplify and write the expression this way. So what I'm trying to do is I'm just trying to minimize or I'm trying to simplify this minimization function here, okay. And by minimizing this minimization function, or trying to simplify the minimizing function using the quaternion, I'm able to help with or reduce the steps of processing. So this is an example of how the registration results looks like, okay, after the ICP approach. So remember, this is a rigid registration approach, and we can see how the different intensities over here actually determine how much is what is the relative position of the different surfaces. Okay, we also see how the surfaces are correctly computed or estimated here. Okay, now here this is the final topic that we'll be looking at, that is Kinect. So I will leave this Kinect topic as a reading exercise for you. But I'll just give a very brief introduction to the Kinect sensors. So basically the Kinect sensors have been developed by or it has been used for the Xbox 360 gaming. And this particular sensor, the importance of the Kinect sensor is that it helps to give very accurate depth map as well as colored images. Okay, so it has got both depth information as well as the color information of the object, and it helps with estimating the pose, that is the position of the objects which are present, and that helps with tracking also. And accuracy is one of the very important. Accuracy as well as a quick result are some of the important advantages of using a Kinect sensor. Now it has got three different sensors here. One is the infrared projector. It has got a color camera as well as an infrared sensor. Okay, so this color camera is used to obtain the RGB image of the particular scene, and here the infrared sensor and projector is there. That means you have a transmitter, and the infrared rays are reflected from the object and reaches back, and the sensor senses that. So from that, what we get is the range information or the range data. And this is an example, okay, where you have the color image as well as the depth information, and both of them can be combined together to get an depth info. So it's not just the relative depth info, but also you will be able to distinguish between the different objects. You are able to distinguish between the person as well as the background and so on. Okay, so this is another example of the Kinect image, right? So this is the color image that is given, and this is the depth information. So here also we see how it is able to, if you look at the chair, it is able to correctly identify the chair or separate segment the chair out from the background. Now, this is a system overview of the Kinect sensor, or using the Kinect camera. Okay, so here, for the RGB D, it's called as the RGB D because it has got both color images as well as the depth information, right? So there's an RGB camera from which a color image as well as a range depth image is taken. Okay, now from these images, certain features are calculated, the sparse features as well as the dense point cloud information are extracted, and from these features what is done is basically a registration is done, a rigid registration using the ICP is done. Okay, so first a ransack is done where the outliers are identified and removed, and followed by an ICP. Okay, now after doing a rigid registration, then it goes for optimizing, trying to optimize the results, and then finally create a circle map or point cloud maps. Okay, or basically it is trying to reconstruct the image. Okay, and this happens from a frame to frame alignment. Okay, so this is just the basics of the Kinect sensors and the Kinect camera. So you can, the rest of the information, if you're interested to know more about the Kinect sensors and its application, you can go through the reading material which I will be uploading separately. Okay, as of now, this is the only information that you need to know regarding the Kinect sensors as well as the range data. Okay, so what we have discussed so far is regarding what is range data or a range image, how is range data segmentation done, that is edge detection. We saw that that there are the edge models are of different types. You have the step edge and the roof edge. We saw how we define the step edge and roof edge. We saw a technique by which you can detect the step edge and roof edge. Okay, so basically the technique is by using the computational molecules method, right? So it has got different computational molecules which are basically linear kernels. These are combined together to form an averaging mask which is used to convolve over the image. Okay, and to find the first derivatives, you make use of the finite differences, that is to find the Gaussian curvature. Okay, and once you have the curvature model, you can easily model the surface there. Okay, and basically you're able to detect the edges also, right? And we saw some examples there. Then what we saw is about the image registration using ICP, that is a rigid registration method, and the steps is the same where you first try to the iterative process of finding the closest points, followed by the estimating the rigid transformation, and then calculating the error, and then again finding the closest points of the correspondences, and this iteration keeps on increasing. That whole process is the same, but what is the exact method by which the closest point is detected or the rigid registration is done is different. And for rigid registration, in order to simplify the equation for finding the error or the distance, we make use of the concept called as quaternions, okay, which helps with simplifying the function which is used, or the minimization function used. And we also looked at the system overview of Kinect. So by this, we end all the topics for the MGCV course. If you have any doubts or if there is any clarifications that you want to know, please feel free to either mail me or send me a private chat. Okay, or if there is any doubts, you can get in touch with me anytime. And that's all. So thank you.